Hey guys, this is me, Rob, and this is Pivot, the device that I am presenting you now. In this short video, you see how Pivot enables grasping virtual objects anywhere in space. But first, let me tell about how we came to the idea of this device. In virtual reality, there are two very different approaches for providing haptic feedback. One is using haptic VR controllers, and their main advantage is that they move with the user's hand, not limiting their operation space. On the other hand, there are encounter type haptic devices that are rendering natural touch and grasp sensations to virtual objects by also leaving users' hand free when needed. Their only downside is that they are often limiting the motion space. With Pivot, we try to combine the benefits of these two approaches. It provides haptics anywhere in space, just like handheld controllers, while still allowing for natural freehand interactions like with haptic proxies. Let me briefly explain how Pivot works. The device is mounted on the user's forearm with a flexible cuff. It has a generically shaped handle that is pivoting around the motorized hinge. This simple design enables three key features. First, rendering grasp to handheld objects. Second, catching and throwing fast-moving objects. And rendering dynamic forces such as inertia or springiness. So the most straightforward functionality is grasping virtual objects, as you see here. As the distance between the virtual hand and the apple is shrinking, the handle pivots into the palm. At the moment when the user grabs the handle, Pivot sends the signal to the virtual hand to also close the fingers and grab the apple. This way, Pivot also serves as an input device for touch sensing. Next, catching and throwing requires essentially the same mechanics as grasping. However, the action time to catch a flying object is orders of magnitude shorter. To overcome the natural physical limitations to make the mechanism extremely fast, Pivot continuously checks if an object is flying towards the hand, and if one enters the activation radius, the handle starts to move already in advance, accounting for the latency and approximating the right moment of collision. And here you see my humble attempt to juggle with two apples. I have to admit I did cheat and reduce gravity. The third key functionality of Pivot is to render dynamic forces. As the branch bends down while plucking the apple, Pivot drives its motor in the direction of this force, effectively pulling the handle outwards of the user's hand. While Pivot has only one actuated joint, the rendered force is always projected onto this axis. And at the end, when the apple plucks, the motor stops pulling, and additionally, there is a built-in voice coil actuator in the handle that plays a thud vibration. This force rendering capability can be then applied to any types of forces, for example, holding a wiggling bunny, or enabling bimanual interactions by coupling the two hands via synchronized push-pull forces. To evaluate these three key features of Pivot, we have conducted a user study with three specific tasks. First, participants rated the realism of grasping objects with different shapes and sizes. Second, they evaluated catching and throwing balls with different velocity and from different directions. And lastly, they sorted 3 billiard balls by their weight. For more details about the results, please refer to the paper. Finally, I would like to show a couple of details about the hardware. So what you haven't seen yet is that apart from the motorized hinge, the device also has a passive radio owner hinge, enabling more agency over the held object. Additionally, the handle also features a push button that enables Pivot to act as an on-demand controller, or as a torch in a VR scene. And with this, I would like to conclude my talk and thank to all my co-authors for this fantastic collaboration and for the opportunity at Microsoft Research to do this exciting project. And thank you for listening and happy to discuss more. Bye bye.